So as most of you probably already know, Python is a very slow programming language. And 90% of the time that doesn't really matter, but for the remaining 10%, it actually does matter, specifically when it comes to scientific computing like machine learning. The way Python solves this problem is by basically not use Python, and it is done by calling another program which is written in a faster language like C, C++, Rust, Zig, whatever, and let that programming language run the code and simply return the result back to Python. There is some overhead when you go this route, but it is still way faster to run the C code this way than running the algorithm directly using Python. For example, this is what NumPy does, and the reason why NumPy is so fast is that the algorithms are not written in Python, they're written in C, and Python just simply calls those functions. Another example is Polars, which is in my opinion the better pandas alternative. It is written in Rust, and also another reason why Polars is so fast. So as I mentioned before, specifically for scientific computing, you need to run a lot of linear algebra. And Python itself is not very good at linear algebra because that requires a lot of loops. What we have instead are GPUs and TPUs, which are very good at linear algebra, so they can run a lot of matrix multiplication very fast. But the problem is that Python cannot be directly run on GPUs or TPUs. So what you would do instead is, again, use Python, compile it to something, and then run that on your accelerated hardware and then return the result back to Python. And herein also lies our goal. We want to write good code that fits our machine learning library. So in other words, we want to optimize not necessarily the Python code, but instead the intermediate code before it gets run on the accelerated hardware. And that is especially the case when it comes to JAX, because in JAX, you don't really care about the Python code all that much. Your goal is to use Python as a front-end language in order to compile it into something else. In the case of JAX, you first compile Python into a JAX expression, which is an intermediate representation. And we will see an example of this in just a moment. And then this JAX expression, this intermediate representation, is then further compiled into a lower representation, which is called XLA. And then this XLA code is then compiled into whatever your desired hardware is. So if you run it on the CPU, it will be compiled using LLVM. For GPU, you will either use ROCm or CUDA, ROCm being the AMD software. And for TPUs, Google's Tensor Processing Units. I'm not exactly sure what they use. I think it's called Mosaic, but that's basically the goal. You want to use Python as the front-end language to write good JAX expressions, which then get compiled into good XLA code, hopefully, and then this gets compiled into the code for your endpoint. And theoretically, you didn't actually have to write Python. You could just start with JAX expressions directly, and JAX offers some capabilities for that. But JAX expressions are not so easy to write. And similarly, you could also skip JAX expression and go straight for XLA code, but that's even harder to write. So you rely on this path of using a, in my opinion, very beautiful language like Python, and use Python as a door to get to these intermediate representations. So to summarize, in JAX, your goal is to write Python code, which gets compiled into good XLA code or efficient XLA code, which then in turn gets compiled into whatever your hardware is that you're running your code on. And now we can go to our editor and see all of this in action. Okay, so first, before we go into detail about JAX's internals, I first want to show you how you would interact with JIT on a day-to-day basis. And JIT stands for just-in-time compilation, and it's the J in JAX. So as a high-level overview, jax.jit basically follows this path, and at the end you get a compiled function which is optimized for your hardware and runs way faster than your normal Python code. So in order to use this just-in-time compiled function, you first have to call the jax.jit function. And it's as easy as giving your function that you want to compile to this jax.jit function. And there are many other inputs that you can give this JIT function, and we will talk about those at another time. For now, this is the easiest way to create this JIT function. But so far, nothing has actually happened because this JIT function only sort of prepares your function for being compiled, but it doesn't actually compile it until you use this function. So this JIT function gets a function as input and returns another function. And now if you call this new function, only then the compilation starts. And this is the output from our JIT function. So let's make this a little clearer. Let's time the duration it took for each of these function calls to happen. So as you can see here, it took around 117,000 nanoseconds to run this JIT function. And then it took another, I don't know how much this is, nanoseconds to run the JIT function. For comparison, let's measure how long a function takes to run if we don't use this JIT function. And here we can see that the non-JIT function took way longer than our JIT function. But this doesn't actually show the strength that you get from compiling your function. That only becomes evident once you call it a second time. As you can see here, the second time our function ran was way faster than our first time. And the reason for that is that the actual compilation of the function happens the first time you call the function. So the first time we called this JIT function, it compiled the function, which is why it took so long. And then the second time we already compiled this function and we were able to use the cached version, which led to a way faster execution of our code. And one neat trick to figure out if your function gets compiled or not is to add a print statement here. And what will happen is that on the first run of this function, so over here, the first time we call this function, we will see the print statement, but the second time we call the function, we won't see it anymore because then we're using the optimized compiled code, which was cached from this first run, and that code will not contain this print statement. And as you can see, we see this print statement only the first time. The second time around, it's not there anymore. And the reason we don't see it the second time is that JAX, when it compiles the function, eliminates every side effect. And this print statement is a side effect. And it needs to do that because compiling your function requires the function to be pure. And a print statement in your function is not pure by definition. What happens if we change the shape of the input of our function? We actually didn't define the shape over here. We simply gave it some values in here and JAX seemed to work with it, but we don't specify the shape here in any way. So if the shape of our function's input change, then what do we expect to happen? So let's change the shapes here and see what happens. So now the second time we run this function, the input shapes will be different than what we had before. And if we run the function, we can see that the function gets compiled 2 times. And the reason it gets compiled 2 times is that the input of this function changed. And by changing the input to this function, we change the JAX expression, which we will see in a moment. And that means that a different compiled XLA code will be generated. And this is especially helpful in situations where your code, for example, becomes very slow and you don't really know why that happens. A reason for that can be that your function keeps getting recompiled because the input shape of your function changes. So when I'm writing JAX code, I usually have a print statement somewhere in my function just to make sure that it only gets compiled one time. So to summarize, when you're writing a function that you want to compile, make sure that the inputs to your function remain static when it comes to the shape and the data type. But there are also other things that you should avoid. For example, let's have a look at this function. This function right here now is a normal Python code. So I can run this no problem like this. And as you can see on this first print statement here, we got a normal output. But then when we tried to compile the function using JIT, we got an error which said attempted Boolean conversion of traced array with shape bool. This concrete value was not available in Python because it depends on the value of the argument x. This is another thing to keep in mind. This JIT operation here worked perfectly fine. We got the duration it took for this function to run, but the error only occurred after we called this function. And then JAX complained that the concrete value was not available. And the reason for that is that our function here changes the return type based on the argument x, and that can change during runtime. So when you want to use these kind of control flow mechanisms, you need to use the built-in JAX functions. For example, select where it selects between two branches based on a Boolean predicate, so kind of similar what we want to do here. But also this function has a few things that you should keep in mind, which is that the arrays that you give here as input need to have the same shape. But for our example here, this select function wouldn't even help us all that much because the return shape here is different than the return shape of this branch, which means that this select function wouldn't work either. And this is what I meant earlier when I said that we need to write good XLA code and not good Python code. This is perfectly fine Python code, but it's not good JAX code. And we need to optimize our functions for them to become good JAX code and not good Python code. So I mentioned earlier that the way JAX works is that it takes your Python code, converts it into this JAX expression, which then gets compiled into XLA, and then finally it gets compiled for your hardware. But now let's actually have a look at what this JAX expression looks like. So we can use the function make JAX expression from JAX, give it our function as input, and then also give it some example values for our function. For example, that can be 1.2 and 4.2. If we print the expression, we can see something here in the console, and this is the JAX expression that gets generated from our function. And I won't go into too much detail here what this means, but as a high-level overview, your function gets compiled into this JAX expression language, which uses primitive operations to describe your program. In this example here, we have two inputs, A and B, and those are float 32s, and then we have another variable here, C, which is also of type float 32, and that is defined as this .general primitive function, which gets as input A and B, and then finally this JAX expression returns C. What happens now is that JAX takes this JAX expression, compiles it to XLA, and then finally to whatever hardware you're running. But one thing you don't see here is the concrete values of the input. Here we said 1.2 and 4.2, but we don't see any of that here. And the reason for that is what we have here is basically just a description of a function. And once that function gets compiled, we can call that with concrete values, and we can be sure that that function will work because it was generated based on example input here. So it takes the shape and data type that we pass it here as input and then compiles a function that specifically works for this input. It won't work on any other input. And we can see that if we actually try to generate the JAX expression and giving it a different shaped input. And as you can see, the JAX expressions here are different. In the first example, there is no shape in here, but in the second example, we can see that now we have some dimensions. And what we learn from this is that each of these JAX expressions gets compiled to a different function. And this also goes back to our JIT operation we had earlier, where the function got recompiled when we changed the input shapes. And now we can see why, because since the input shape changed here, the JAX expression changed, which meant that JAX had to recompile this function. So it's important when you work with jax.jit that you make sure that whatever function you are compiling has static inputs and you don't call it with any other input shape, because that will recompile your function, and it's generally not what you want. And as another rule of thumb, you want to put as many operations as you can inside a JIT block. And you can add a JIT decorator here, and this will call jax.jit on your function automatically. And when you do this, try to get as many JAX operations as you can inside your function that needs to be JITted. Because the more JAX operations you can fit in your functions, the better the compiler can optimize your code. Of course, that won't always be possible, and then in those situations you might have to split your function into smaller chunks and then JIT compile those. But in general, try to get as many operations as you can inside your function. So to summarize, you can create a JIT function by passing your function, which needs to be pure, to this jax.jit function. Then if you call the returned function, it will then compile your function and cache it, and that will be okay fast. But then if you call it the second time, it will use the cached version, and that will be super fast. And as a rule of thumb, you want to get as many JAX operations as you can inside your function. And that's basically it for jax.jit. We will see other JIT flavors when we talk about Equinox and Flex, but that will come at a later time. And I think this was enough for a good introduction into jax.jit, and we only managed to scratch the surface of what you can do with jax.jit, especially when it comes to running your code on multiple GPUs. But we will look at that at some other time. For now, if you have any other questions, make sure to post them into comments, and I will try to answer them as quickly as I can. So I really hope you enjoyed it. Thanks for watching, and I will see you in the next one.